Okay, we want to look at areas enclosed by the y-axis. In this case, we are looking at functions that are a little bit different than what we've done before. Our x is now the subject and y is our independent variable. So it changes the way we graph these a little bit, but our interpretations are very similar. If I'm looking at this first graph here, and I start looking at my lower boundary, that's going to be A, and my upper boundary is going to be B. Because the area is to the right of the y-axis, my area is going to end up being positive once I integrate. Now, if we shift down to the function below it, we still have the same parameters. We're still going to have a lower boundary of A and an upper boundary of B, but the thing that changes is my area is now negative on my left-hand side of the y-axis. If I look at my function or my equation for area of um, between the y-axis, then nothing's really changed. I just change f of x to f of y, change dx to dy. So I'm still going to go for an integral between a and b, so my lower value to my positive value, except now it's going to be y as an independent variable. Graphing these can be a little bit tricky, but that's okay. They've given us the first one, and our first one, they've given you the equation x equals y squared. Now, often our first instinct here is to just square root the y and square root the x, and so that could be fine, but we actually need to be able to have some negative y values here. So if the equations change and x is the subject, what we can do here in this case is create our table of values, but instead of putting in the values we're going to substitute in for x, let's put in the values we want to substitute in for y. And so if I substitute in, I need to make it work a little bit smaller. If I substitute in -4, -3, -2, -1, 0, well, that's going to be a little bit easier for me today, and I can just put it into my function. If I square -4, I'm going to get 16. If I substitute -3 into y squared, I'm going to get 9. If I substitute -2 into y squared, I get 4. -1, I get 1. 0, I get 1. 1, sorry, 0, I get 0. 1, I get 1. 2, I get 4. 3, I get 9. 4, I get 16. Now, when we sketch these in term 2 of year 11, we found out this function looks like a sideways parabola. So it's going to look something kind of like that and kind of like that. So maybe I could have smoothed that out. Ooh, that's not so good. Let's make that better. So we're gonna try one more time. Let's smooth that out. We're gonna go, okay, I'm gonna get this nice parabola going up here. Let's see if I can get it to follow through. It looks all right. Okay, well, they're close enough. Um, so I've got my parabola. I know one of my values for my upper bound is 3 because that was given in the equation. So let's change that color really quickly. Let's change that color really quickly. We'll redo. And I'm going to say 3 is going to be up here. Nice little sketch. And my lower boundary is 1. And so I'm looking for the area between those two. I'm looking for this area here that I'm highlighting now. Okay, well, The sketch was the harder bit. Once I've done that, I know my function is x equals y squared. I know if I want to find my area for that, I'm going to take the absolute value of the integral between a and b for my function in relation to y dy. So in this case, my lower boundary is 1, my integral's upper boundary is 3, my function is y squared, and dy. Let's chuck in those absolute values again. Once I integrate that, I know it's going to be y cubed on 3, but I still need to go in between that 1 and 3. So then I just do what I always do. I don't need y, I need 3. I need 3 cubed over 3, take 1 cubed over 3, and so I'm going to get 27 divided 3 is 9 minus 1/3. So I'm going to get 8.66 recurring units squared from my first one.